So today we're going to talk about PrimeMatch, which is a secure multi-party computation tool that we have in the bank. And it's the first tool we have in the bank that uses full-fledged secure multi-party computation. And it's also the first tool in this field in finance. So let me start immediately with the problem statement. So what was the process before PrimeMatch? So we had this so-called Axe inventory. So every day the bank was sending a list of the inventory to clients. So most of these clients were hedge funds, okay? And then the client was able to choose if they want to trade on something. So this is a fake example of inventory. So here you have the stock and then buy or sell and then the number of shares, okay? So this is what the client sees. And then they can choose whatever they want and come back to the bank and say, okay, I want to trade these symbols, okay? So this is how it was done before. And we were not sending our full inventory to the clients for privacy reasons, okay? So that was a reduced inventory. And there were some other problems. Some clients raised some concerns about potential leakage. So think of this inventory and think that yesterday we bought a very large order from a client. Okay, let's say I bought 1 million shares of Apple, for example. And then the next day I'm gonna add this to my inventory, okay? So the client that I bought it from the previous day, they will say, okay, you are adding this to your inventory. So there's this change now in your inventory. And maybe the rest of the street can tell that you got this from us. Apparently some hedge funds trade more some symbols than others. So, but anyway, as long as the client has this concern, we cannot do anything about that, okay? So there were these concerns about large trades. And of course, as said, this is like a part of our inventory, but still, it has some extra leakage from the JP Morgan side, right? Because it's a reduced inventory, but still, there's still some leakage, okay? So this is like, can I point to this? Oh, okay, good. So this is our whole inventory, the reduced inventory, and then a solution that we also have in production, which I'm not gonna talk about it in this talk, is that we were also trying to reduce this leakage about the clients that they raised using differential privacy. So I'm not going to talk about this now, but it's like differential privacy under continual observation because we publish this every day. But that's another topic. So this is also something else that we have. But today I'm going to talk about the solution where we're actually trying to hide completely our inventory, okay? So we're not sending any inventory in the clear. So this is the focus of this talk. And to do that, so we're going to basically not reveal our inventory. So think that we're going to use a form of secure multi-part computation. Actually, Marcel introduced secure multi-part computation. So what it allows you to do is like before we had encryption. With encryption, we can just encrypt everything and exchange the messages. We use it all over the internet. But what it doesn't allow us to do, it doesn't allow us to compute on the encrypted data. And secure multi-part computation allows us to compute on this data. Okay, so we're going to encrypt the inventory. I'm going to go to the details later in the talk. Okay, so I'm not going to introduce secure multi-party computation, but I'll just tell you the basics. In secure multi-party computation, if we trust somebody, if we have a trusted third party, we can all send our input to that trusted third party. That party computes and send back the result, but we don't want to trust anybody, okay? So in secure multi-party computation, you trust only yourself. So this is the main one sentence that I can say about the tool. Okay, and there was a lot of work. So actually, this tool is not new. It was introduced in the 80s. And there was a lot of research on that to make it more efficient. Okay, and we started having like some applications that use actually efficient secure multi-party computation. And there was this celebrated auction in Denmark where they did some sugar beet auction. If you look at the running times compared to the running times that we have today, there's like orders of magnitude slower. So you can see like how much the field has advanced. Okay, so and actually our implementation is a sort of an auction too. Okay, so here's a particular example, just to give you an idea. So we have the bank. Okay, so here is again a toy example. So by the way, short is for sell and long is for buy. Okay, so this is before the matching. Everything is encrypted, and after the matching, for example, let's look at the Microsoft stock. So here, the client has 300, but the other side has only 200 to give us. Okay, so now after the matching, the client has left with 100, okay? So what we are learning here, so the goal is to only learn the output, okay? For example, I will never know that this client had 300, okay? So I will only know that the matching was 200. So this is the idea. You don't know any values that they are encrypted here, and you only learn the output, okay? So you reveal whatever the output reveals. So this is the guarantees that the system gives us. Okay, and to build this tool, we actually asked the clients. So we went to almost 20 hedge funds, and we were asking like what requirements they want to actually run such a tool. So an important one was that the clients did not want to actually install anything. So that was one of the bigger things. And we had to do actually a web-based app. And in JP Morgan, we have something which is called JP Morgan Markets, which was already like a portal, an online portal that we had. But it was mostly used for downloading and uploading files. So we had to do a lot of things there to integrate our protocol there because it's an interactive protocol with many rounds back and forth. Okay. Then we also want to do it efficiently. Okay. We don't want like to run this auction and wait for many minutes. So it's not high frequency trading, but still we need to do it fast. Okay. And then we also want what is called malicious security. So malicious security means that even if the parties deviate from the code and the protocol, they can still not learn any information about the other parties' inputs. So this is very important for both the bank side and the client. So both of them, even if they deviate from the protocol, we have guarantees that nothing is revealed. Okay. And then we also want, we want to make the JP Morgan inventory like available, like the full inventory. Okay. So what we put in the system is our full inventory. Okay. So I'll talk at the end if I have time about the implementation more, but these were some of the challenges that we had. Oh, why did it go at the beginning? Okay. That's weird. I guess I pressed something here. And there's also, so what I showed you so far was enabling matches between the bank and the clients. But what we can also do that was not possible before was to actually match clients together. So let's say we don't have an inventory, okay? So let's say Daniel is asking for Apple, but we don't have Apple. I'm the bank and I don't have to give him Apple, but maybe Sahar has, okay? So now I can match them together, okay? So before I wasn't able to do anything like that, right? I had no clue about their inventory. Now I have it, but I have it encrypted, okay? So now I can enable this match. So our application also enables this kind of matching, okay? So here is the model. So first of all, the clients, as I said, they didn't want to install anything. Also, they don't want to communicate with the other clients. Okay, and this is even a bigger problem because we're running this auction every 30 minutes. So you don't even know who's going to show up in every round, okay? So we should not have communication between the clients. So it's like a star topology where basically everybody talks to the bank, okay? So here are the clients and everybody talks to the bank. Okay, and we can also support partial matches, meaning that if you ask for 100 and if we have only 50, we'll give you 50. So that's what it means. The malicious security, and also another one, another requirement which is actually also important is because the clients didn't want to install anything and we did this web-based app. I mean, we should not assume that the browsers are very powerful computational, right? So also the computation of the client has to be like very minimal, okay? And then on fairness, that what I mean here by fairness is that when all the clients come together, we don't want to exhaust all of our inventory to a single client because it will be less fair. The best solution is to run some optimization problem to see how we can allocate our inventory to the different clients. But running optimizations algorithms on secure multi-party computation is not that fast. So I'll tell you at the end, we have like some partial solution to that. It's a greedy approach on how to allocate it. But yeah, we cannot run an optimization like very fast based on the requirements of the system, okay? So I'll give you like a very quick idea on how this can be done using full homomorphic encryption. We are not using full homomorphic encryption because it's very inefficient for the particular task that we want to do here because we do a lot of nonlinear operations. But in general, if you have full homomorphic encryption, which is the idea where you can compute unencrypted data, okay, you encrypt your data in B, then you run any function that you want on it, and then you just get the encrypted results, and then you decrypt the answer, okay? So if we had such a tool, okay, we can apply it very easily to this problem. So here is an example. I'm using the multi-party matching where we're trying to match the clients together. So here is a toy example of like what the clients want to do. Okay, so you can see that we can satisfy 75% of this client using the orders of the other two clients, in this example. Okay, so if you use fully homomorphic encryption, you can just encrypt your orders, you encrypt everything. Okay, and then the bank receives all these orders, and with fully homomorphic encryption, as I said, you can apply any function. So it can find the matches, these are the matches, and then sends back the encrypted matches back to the clients. And then the clients decrypt and see the matches, okay? So this is like how you can do it using fully homomorphic encryption. Okay, but as I said, like doing this matches is basically doing comparisons. So here, think that we are comparing with what is the minimum, for example, between 160 and 50, we want to compute what's the minimum. And this is a nonlinear operation. So FHC doesn't perform well in these scenarios, okay? So we're going to use something which is more efficient. And I'm going to focus only on the secure comparison protocol that I was talking about. So think that we have two numbers and the minimum is the matching quantity, right? So that's what I'm going to focus now. And we have the setting is the two clients and the bank in the middle. Remember, we have the star topology where the clients are not supposed to talk to each other, right? Okay, so first I'm going to talk about 2 out of 2 secret sharing, which is like a very basic concept in cryptography. So what you can do with this secret sharing, basically you can take your secret and split it in multiple parts, such that you need all the parts together to actually recover your secret, okay? And there are many different versions of it where you have different thresholds. In some cases, you don't need all the shares to reconstruct, you need like T of them. But here I'm going to show you the 2 out of 2 to make it like very simple. And that's actually what we're using in the implementation. So every party takes their secret value. Here, think that this is like the number of the shares that they want to trade. Okay, so they split it in 2 parts. And then they exchange each share. Okay, so the first party gives his second share to the second party. Okay, and likewise, the other party does the same. And here I'm showing a simple secure aggregation. And let's say they add the shares and they send these numbers to the bank, okay? And the bank, if you add the shares, you will actually get the sum of A plus B, okay? And the bank will only learn A plus B without learning anything else about A or B, okay? So this is a simple example for like adding values. And what we are doing here, we actually, instead of like adding, and instead of doing addition, we want to do this comparison, okay? We want to find which one of the 2 values, A and B, is bigger, okay? So I'm not gonna go into the details on how like we do it. So since we want to do the comparison, it's not just a simple addition of shares. It's basically all this expression here. I'm not gonna go to the details of the expression. So this is, we are starting as a base to use the protocol of this work on secure NN. So they had a secure comparison protocol. However, we improved it in 2 ways. So this protocol here is nonlinear. So they required to do multiplications, okay? And every time you want to do multiplications with this approach, you need to communicate, okay? And as I was saying earlier, I want also to eliminate the communication. So we changed the protocol to only have linear operations. So essentially we built a non-interactive protocol here. So we can actually run a secure comparison where basically it's a one-run protocol with no interaction. So this is the improvement that we did over that work. And also we added malicious security too. So that's another improvement that we have over that protocol. So I'm not going to give the details of this expression, but remember that per bit of these numbers that we want to compare, we calculate a value, okay, a value D. And if there's a single D that is a 0, it means that A is bigger than B, okay? And if A is bigger than B, then the matching value is B, which is the minimum, okay? So that's all we need to remember for the rest of the talk from here, okay? So let me just give you like the idea of the semi-honest protocol. What I mean by semi-honest protocol, I mean that it's not malicious. So what do we do? So again, we have the bank. So we are using this secret sharing approach. So the parties secret share their volume. And by the way, we're also hiding the simple and the side, but I'm dropping it here on the slide for the sake of simplicity. So we're focusing on hiding the volume here on the slide. So they exchange the shares, and because they're exchanging them through the server, they also encrypt them, okay? So that the server doesn't see the shares, because if it sees the shares, it can actually leak some information to him. So they exchange those shares, and then they run this function that I told you earlier that computes the minimum, okay? So they both run it, but we run it on the shares, okay? And then I told you that computation here is linear, so you can actually run it without extra interaction. So they run it and they get these outputs. And now they are sending all this. So we have as many Ds as the bit length of the numbers. And if there is and then we reconstruct, so the server gets this share, so everything is on a shared form, okay? And to go back to the answer, you need to bring the shares together, okay? And for that particular circuit, we just need to do a simple addition at the end, okay, here. So if there's at least one D that is 0, then it means that A is bigger than B, what I was saying earlier. And that answer is reconstructed by the server. Okay, and if there's a match, he's pinging the parties, telling there's a match, and the parties reveal their quantities. Okay, and another important thing is that the parties, when they come to the auction, they have to commit to their inputs. Okay, they should not lie about their input, because if we say that there's a match, and then instead of A, they open A prime, another value, I mean, then that's not desired, right? And maybe there's no match anymore, because if A prime is bigger than what the other party has, then the clients are messing up with the system, right? So you also need to commit to the values, and there's this cryptographic commitments. I'm not going to give you details, but they allow us to commit to particular values that we cannot change later. So that's another step that we have to do. So the parties need to commit. And for example, when we have like the matches, the clients also open their commitments to actually verify that that was the real value that they had, okay? So a few words about malicious security. How much time do I have left, Daniel? Okay, okay. So how we can do malicious security? I mean, I'm gonna say this in 1 minute. And I remind you, malicious security means that the client doesn't run this correctly, okay? They run something else. Okay, or they flip some bits such that to learn some information about the other part. So you can think of any arbitrary behavior from the clients. Okay, so they can misbehave here. So one thing that you could do, you can actually apply this dual execution, that's called, meaning that you run the protocol twice. Okay, so here I'm adding a second run where both of them are running it on the other shares. Okay, so you see here, like this was run on the first couple of shares, and then we can run it on the second type of shares. But immediately you will think now, okay, if you have both shares, then you have, like, if I have A1 and A2, actually B1 and B2 from the other client, I learned his B, right? So I cannot really run it twice because I can learn his input, okay? But what we are doing to run it twice, so basically think that I'm repeating the computation that this guy is supposed to repeat. And at the end, I'm checking if he ran it correctly because I also ran it. So we can cross-check if it was run correctly. But as I said, we cannot have the shares because then I learned B. But what we can do, remember I told you that the parties commit to their values, okay? So we can run the second thing on committed values, okay? You cannot see inside the commitment what is in there. So you can actually run the second part on commitments. And you need homomorphic commitment, just actually linear homomorphic commitments, which are pretty efficient. So you can run the second execution using the commitments. And because our protocol, remember I told you it's non-interactive and linear, you can use these commitments with no interaction too. So you run these both interactions, and then basically the bank can cross-check and see if the results from both executions are the same. I'm hiding a lot of details here under the carpet, but think that the server can actually cross-check these values, okay? And the last part that I want to say about the solution is that now you need to check that all of these commitments are consistent too, and also check that the server is not lying, okay? So when the server is supposed to check, maybe he can also lie. Maybe he can say, actually, there's no match, okay? So he can start also lying about what's happening in the computation. And we could use zero knowledge proofs. By the way, you can throw zero knowledge proofs in general from the beginning, also to compute this function here, but it will be very inefficient, okay? So zero knowledge is like a very sensitive tool that it can very quickly become very inefficient. But we were able to use like efficient zero knowledge proofs, and particularly here. So to check the server, remember I was telling you that there are all these D values, and there's, if A is bigger than B, there should be a single D that it's actually 0. And for this one, we can have an efficient zero knowledge proof where the statement is relatively simple. It's from all of these committed values. we want to show that there's actually at least a commitment, which is a commitment to 0. And trust me now, but zero knowledge proofs for this statement are actually very efficient. Okay, so this is the kind of heaviest zero knowledge that we're using here. ZK what? There it's like they're more complicated, the zero knowledge proofs that they use there. But there are many different types of zero knowledge proofs that you want to use for the rollups. So think that this is a much simpler version than what is used there. Yeah. Okay. So that was about the solution.
This is a good question. So the clients have the commitment, right?
The what?
The clients have the commitment.
Yes.
And the bank is doing a statement of the document.
Yeah. So you're receiving the commitments. So they're committing to all their values. They're committing to the actual value and the bits. So you also need to check the consistency of that. So the client gets the commitment, and the client the client needs to add. Okay. So he does the addition and he ends up with commitments of the Ds. So he's proving stuff about the commitments of the Ds. So he has commitments.
Make sure that both clients get the same commitments because they are related by the bank.
Yes.
So you make sure the bank doesn't lie in the bank.
The clear text answer?
Because
so you are actually, so it's on top of, so these are also committed values, okay? So remember, like the first one is not committed, but the second one is committed. So I'm actually generating the commitments on the D from the commitments of the other parties. So they can actually check. And also there's a thing that we have to do here about the randomness, because when you do that, the randomness that you use for the commitments is not yours, it's from the other clients. So you need to run actually kind of like a secure computation on the randomness because the server doesn't have it. So that's like the tricky part there, exactly. Because he doesn't have the randomness. Okay, so I'm gonna show you like some screenshots of the demo. So here's the JP Morgan markets. So I'm going to show you the client side. Okay, so think that I'm a client and I'm like logging into the system and I'm trying to participate in the auction. So I'm logging into this JP Morgan markets, and then this is like the first screen that the clients see when they enter the tool. Okay, so at the beginning, they need to upload their actual file with the trades. So here the client has uploaded his symbols. I mean, obviously I have test symbols here. Okay. So this is the client is uploading all of the symbols. So these names here are like different systems that represent the same symbol in different ways. Okay, so we want to make sure that this is actually the real stock that we're talking about. It's not another stock. So we need to incorporate all these different systems. And then this here is the direction, whether it's long is for buy and short is for sell. And then actually going back to this fairness thing, here I can tell you what we are having in production to accommodate this fairness issue. So the client submits two values. He submits a minimum value that he is willing to trade and a maximum value, okay? And what we're doing, after all the clients submit, we first go over all their minimum quantities. And if we exhaust our inventory, then we stop. But if we still have inventory, then we go back to the clients and look at their maximum quantity. So in that way, you could say that, okay, because I'm looking first their minimum values, I have more chances to give more inventory to more parties. But of course, that can be the first client who, again, gets completely everything, okay? So it's not like a completely guaranteed fair solution. It's, as I said, it's a greedy approach, and that was the best we could do in this case. Okay, and then we have here, as I said, this is the screen of the client while he's uploading it on his browser. So that's what the status register means. And here, I mean, you can see here like the time, and then it says, so we give some time to the clients to come and submit their orders. Okay, so we call it axe registration. So after this time, we are doing the matching, okay? And then like we output the results, okay? But it's like, you can see the times later, but it's almost instantly, okay? So, but we give like some time for the matching here. So this client in the screen, he came, he uploaded his trades, okay? And here you can see how much he sent, and some of them, like some of the securities or symbols, they were not recognized by our system. We also need to kick out things that either we don't have or they're fake symbols, okay? Okay, and now you can see that we move to the next step, which is the matching, okay? And now it starts doing the matching here. So this is a screenshot I got while it was computing it. And as I remember, I was saying that first it goes from the minimum value and then it goes to the maximum value. So you can see here, as it goes through the minimum values, we start getting some partial matches here. And let's find an example. So, okay, so for example, here we see, is this 20? Yeah, so we give the full minimum quantity to this client already. It's a partial match, okay? And here is actually the end of it. So for the first one, for example, we can see, so what was the, it was this one, I think. No, I think the screen is different here. Wait. They're the same. So this is NA2. NA2 is actually this one. So actually we can see that we gave 330, okay? So we didn't give the full maximum quantity. So we give him all the 20 that he had in his minimum. And from the maximum, we were not able to give him his full maximum. We only give him at the end 330. It's 330, right? I cannot, or 300. I cannot say. Okay. And at the end, we have the price actually, where the price is like fixed and it's public in advance. Okay. So this was the demo, and we are running this every 30 minutes. Okay. And again, just to conclude, so we have this capability of either matching the clients with our inventory or the clients together. And the tool is running in production. And if you have any questions, please feel free to. Yeah, sure. Yeah.
You mentioned that a proper optimization algorithm to be in efficiency. Is there any evidence that this is enough? Or like, is there a push to actually build an app?
So they do want to actually have a more fair solution. And we told them that optimization is not, like, you cannot run it in seconds, okay? We are also trying to make faster optimization. But now a solution that we are looking is to tier the clients. So based on how much they trade with us, and have different tiers, and then go first with these clients. And then we can also see their history of their volume. So we can tell how much they are usually trading. So we can actually start filling up the clients that they don't have huge volume. So this is some other thing that we're trying to do currently. But yeah, they do want to make it more fair. Yes. And it's an interesting open question. Yep.
How about pricing? It's client to client, aftermarket. Is there actually more creativity?
So this is the spread that you have here. So the more matches that we can have, the better spread we can give. So yeah, so the more we have, we can actually reduce the spread, and then the clients will like to trade here more because the spread will be better. Yes. Yes.